Imagine a place in the universe where time runs backwards,
where instead of consuming everything that approaches, it violently expels matter and energy into space, where the laws of physics as we understand them reach their breaking point. And don't forget to like, it fuels the journey forward, light and steady. In 2006, astronomers detected something extraordinary. A gamma-ray burst designated GRB 060614 behaved unlike anything they'd ever observed. It lasted 102 seconds. It emitted no supernova signature, and its energy distribution defied every model of stellar death we possessed. Some physicists whispered a possibility too radical to publish. What if we'd witnessed the first white hole? The mathematics have existed since 1916, buried in Einstein's field equations. Subscribe to the channel, your click is a small spark that helps this place grow. The physics demands their existence. Yet for over a century, mainstream science dismissed them as mathematical curiosities, solutions to equations that couldn't possibly exist in nature.
But recent observations are forcing a radical reconsideration. What if the universe contains objects that expel rather than attract? Regions where causality itself breaks down? Gateways that connect to other universes or to the infinite past of our own?
Today, we journey through evidence that challenges everything we thought we understood about the fabric of spacetime itself.
Consider the possibility. Examine the evidence. Question what you know. Prepare yourselves. We begin.
In November 1915, Albert Einstein published his general theory of relativity, a complete reimagining of gravity not as a force, but as the curvature of spacetime itself.
Within months, a German physicist named Karl Schwarzschild was solving Einstein's field equations from the trenches of World War I.
Schwarzschild discovered something unexpected. The equations contained two solutions.
One described a gravitational singularity that pulled everything inward, what we now call a black hole. But the mathematics revealed a mirror image. A second solution where time reversed its arrow. A singularity that expelled everything outward. He called it a white hole. Think of it this way. A black hole has an event horizon you can cross in only one direction, inward. Once you pass that boundary, all possible futures lead to the singularity. No force in the universe can pull you back out. Not rocket thrust. Not light itself. A white hole reverses this entirely. It has an event horizon you can only cross outward. You cannot enter a white hole from the outside, just as you cannot escape a black hole from the inside. The white hole's past is sealed off, inaccessible. Matter and energy fountain outward from its horizon, ejected into the universe with nowhere to go but away. The mathematics were perfect. The physics seemed impossible. The dismissal, 6 to 10 o'clock, for decades, physicists treated white holes as mathematical artifacts. Curiosities that satisfied equations but violated physical intuition. After all, the universe we observe runs forward in time. Entropy increases. Systems become more disordered. Heat flows from hot to cold, never the reverse. A white hole seemed to violate thermodynamics itself. How could something continuously expel matter and energy without a source? Where would the material come from? What mechanism could sustain such a fountain? Einstein himself never mentioned white holes in his later work. When black holes were confirmed in the 1960s and 70s through X-ray observations, white holes remained absent from the observational record. Theorists assumed they were mathematically possible but physically forbidden solutions that the universe simply chose not to implement. But then physicists began exploring the full implications of Einstein's equations. In 1935, Einstein and Nathan Rosen discovered that black hole solutions could connect to somewhere else through what became known as Einstein-Rosen bridges, wormholes. The mathematics suggested that every black hole's singularity might connect to a white hole's singularity. The black hole consumes matter in one location. The white hole expels it in another, or another time. Still, no one took it seriously. The calculations showed these connections would be unstable, collapsing faster than light could traverse them. Theoretical but useless. Possible but pointless. Then in 2014, physicist Carlo Rovelli and his colleague Hal Haggard published a paper that changed everything. They'd been working on loop quantum gravity, a theory attempting to merge quantum mechanics with general relativity. Their calculations revealed something extraordinary.
When you apply quantum mechanics to black holes, they might not be eternal prisons.
They could evaporate. And in evaporating, they might transform. The math suggested that what we call a black hole could be one phase of an object's life. Given enough time, perhaps longer than the current age of the universe, a black hole could quantum tunnel through its own singularity and emerge on the other side as a white hole. The consuming void could become an expelling fountain. Suddenly, white holes weren't just mathematical curiosities. They might be the future state of every black hole in existence. Or the ancient relics of black holes from the deep past. Rovelli's team calculated the timescale for this transformation. Roughly 10,100 years for a stellar mass black hole. That's a 1 followed by 100 zeros. Incomprehensibly longer than the current 13.8 billion year age of our universe. But the universe contains black holes of all masses. Primordial black holes formed in the first second after the Big Bang might be much smaller. And smaller black holes transform faster. Some could be completing their transformation right now. The predictions were specific, observable, testable. But the evidence forces us to confront an uncomfortable possibility. That we've already been seeing white holes for years without recognizing them. Gamma-ray bursts rank among the most energetic events in the universe. For a few seconds, a dying star releases more energy than our sun will produce in its entire 10 billion year lifetime. We've detected thousands of them. We understand their patterns. Until we don't. In April 2006, NASA's SWIFT satellite detected GRB 060614. The burst lasted 102 seconds, long enough to classify as a long-duration burst. Every long-duration burst ever observed has been associated with a supernova. The explosion of a massive star triggers the burst. We see the supernova's light arrive days or weeks later. GRB 060614 produced no supernova. None. Astronomers searched for months with the most powerful telescopes on Earth. Nothing. The burst appeared from a location with no massive stars, no stellar remnants, no plausible source for a conventional gamma-ray burst. The energy distribution was wrong too. It released about 1,051 ergs, equivalent to converting the entire mass of our sun into pure energy in less than 2 minutes. But the spectrum didn't match any stellar death model. The gamma rays arrived in a pattern that suggested a compact object violently expelling material that had been compressed to enormous density. In 2015, astronomers detected a similar anomaly. A fast radio burst that repeated at irregular intervals from a fixed location in space. FRB 121102 released millisecond-long pulses of radio energy equivalent to what our sun produces in an entire day. Over 3 years, it fired off dozens of bursts with no discernible pattern. Conventional explanations involve magnetars, neutron stars with ultra-strong magnetic fields. But FRB 121102's bursts showed a peculiar characteristic. The radio frequencies were dispersed in a way that suggested passage through extremely warped spacetime near a massive compact object. One team calculated that the dispersion pattern matched predictions for material being ejected from just outside a white hole's event horizon. In 2013, the European Space Agency's Planck satellite completed the most detailed map ever made of the cosmic microwave background, the afterglow of the Big Bang itself. This radiation filled the universe 380,000 years after creation, when matter cooled enough to become transparent. It should be almost perfectly uniform. It isn't. The Planck data revealed a cold spot in the constellation Eridanus. This region spans about 1.8 billion light-years across and appears 70 microkelvins colder than the surrounding sky. That's not much, 70 millionths of a degree. But at cosmic scales, it's enormous. Standard cosmology predicts variations of perhaps 18 microkelvins. The cold spot is 4 times larger than it should be. Over 2 decades of observations have confirmed it's real and persistent. And crucially, it's not empty.
It contains galaxies and normal matter. It's simply colder than physics allows. In 2017, researchers at the University of Durham proposed a radical explanation. The cold spot could be the imprint of a bubble collision where our universe brushed against another universe during cosmic inflation. The collision would have left a mark in the temperature map. But there's another possibility the team mentioned but didn't emphasize. The cold spot's characteristics precisely match predictions for the gravitational signature of a white hole that formed during the inflationary epoch and has been expelling dark matter into this region for 13.8 billion years. The expelled dark matter would create a gravitational void, a region slightly less dense than its surroundings. The cosmic microwave background photons passing through this region would lose less energy to gravitational blue shifting, appearing slightly cooler to our detectors. The math works perfectly. The observations fit. The prediction is testable. Since 2007, astronomers have detected over 1,000 fast radio bursts. Most last mere milliseconds. Most occur only once from any given location. We've traced several back to their host galaxies billions of light years away. But a subset behaves differently. Approximately 3% of detected FRBs repeat. They originate from the same location in space and fire multiple times over months or years. In 2020, astronomers made a breakthrough. They localized a repeating FRB to a specific galaxy and performed detailed observations with multiple telescopes. The source resided in a region with no star formation. No young stars. No supernova remnants. No magnet Rs. No black holes feeding on companion stars. Nothing that conventional astrophysics predicts could generate such energetic radio pulses. The bursts arrived with a peculiar chirp, high frequencies slightly before low frequencies. This dispersion occurs when radio waves traverse plasma, the ionized gas surrounding massive compact objects. But the degree of dispersion was extreme, suggesting passage through matter compressed to densities approaching that of atomic nuclei. A team at the Netherlands Institute for Radio Astronomy calculated the dispersion measure. The radio waves appeared to travel through the equivalent of a trillion kilograms per cubic meter, the density of matter at a neutron star's surface. But they showed no rotation period, no X-ray emission, none of the signatures magnet Rs produce. In 2022, astrophysicist Amir Levinson published a paper modeling white hole signatures. His predictions: brief, intense radio bursts from matter being explosively ejected from the white hole's horizon. Extreme dispersion from passage through the compressed boundary layer. No repetition pattern because the ejection events are quantum mechanical and therefore fundamentally random. The observations match the predictions with unsettling precision. But this represents just one piece of a much larger puzzle. Primordial black holes in the transformation timeline, 25:00-28:30, in the first microsecond after the Big Bang, the universe was extraordinarily dense. Quantum fluctuations in the density of space could have created pockets compressed beyond the Schwarzschild radius, the point where spacetime curves into a black hole. These primordial black holes wouldn't have formed from stellar collapse. They'd have been born directly from the chaos of creation itself. Stephen Hawking proved in 1974 that black holes slowly evaporate through quantum effects at their horizons. The smaller the black hole, the faster it evaporates. A black hole with the mass of a mountain would evaporate completely in the current age of the universe, releasing its mass energy in a final burst of radiation. But Rovelli and Haggard's calculations suggest something different. Before complete evaporation, quantum tunneling could flip a black hole into a white hole. The transition time depends on mass. A black hole with the mass of a large asteroid, about 1,015 kilograms, could complete its transformation in roughly 13.8 billion years. That's exactly the current age of the universe. If primordial black holes formed with this mass range in the first second after creation, they'd be transforming into white holes right now. Today. As we speak. And they'd announce their transformation with a characteristic signature. The final stages would be violent. The black hole would evaporate until its horizon shrank to a critical size. Then quantum tunneling would occur.
spacetime would flip. The event horizon would reverse.
And all the matter that had accumulated inside, potentially billions of years worth, would be violently expelled in a matter of seconds. The energy release would be spectacular.
Gamma rays, X-rays, radio waves, possibly even gravitational waves. The signal would look like a gamma ray burst, but with a characteristic spectrum, one we might have already detected. In the 1970s, physicists identified a profound problem with black holes. When matter falls into a black hole, it carries information, the quantum states that specify exactly what that matter was. According to quantum mechanics, information cannot be destroyed. It must persist somewhere, somehow. But black holes appear to destroy information permanently. Matter crosses the horizon. It falls to the singularity. Eventually, the black hole evaporates through Hawking radiation. The radiation appears to be completely random, containing none of the information about what fell in. This is the black hole information paradox. It suggests either quantum mechanics is wrong, general relativity is wrong, or something else is happening that we don't understand. White holes offer a solution. If black holes transform into white holes, the information isn't destroyed. It's simply delayed. Matter enters the black hole. Time dilation near the singularity slows its experience of time to near zero. From the infalling matter's perspective, it reaches the singularity almost instantly. But from the universe's perspective, it takes an incomprehensibly long time. The matter sits in a quantum superposition at the singularity until the transformation occurs. Then the white hole expels it, information intact. The information wasn't destroyed. It was time-locked, waiting for the quantum tunnel through the singularity to open. Leonard Susskind at Stanford has called this possibility black hole complementarity. The mathematics work. The quantum mechanics are consistent. And crucially, the mechanism makes testable predictions about what we should observe when white holes form. In March 2023, the James Webb Space Telescope detected something extraordinary. A galaxy designated JADES GSZ 13-0 existed just 325 million years after the Big Bang. It shouldn't exist. This galaxy is massive, roughly 109 solar masses. Forming that much stellar mass requires hundreds of millions of years of star formation. But the universe was only 325 million years old. There wasn't enough time. Multiple explanations have emerged. Perhaps star formation was more efficient in the early universe. Perhaps supermassive black holes seeded galaxy formation faster than models predict. Or perhaps these aren't galaxies at all. In June 2023, astronomer Fabio Percucci published an analysis suggesting some of these impossibly early objects might be white holes expelling material from primordial black holes that formed in the first microsecond after creation. The expelled matter would be extremely old, potentially older than the universe itself in some quantum reference frames, but newly visible as it emerges from the white hole horizon. The most remarkable discovery involves gravitational wave observations. LIGO has detected dozens of black hole mergers, events where two black holes spiral together and collide, releasing enormous gravitational waves. The signals match predictions precisely. But in 2020, LIGO detected an anomaly designated GW190521. Two massive black holes, 66 and 85 solar masses, merged in an event that should have been impossible. Stars cannot produce black holes in this mass range. There's a gap in black hole mass distributions between about 50 and 120 solar masses, created by a process called parainstability supernovae. Yet here were two black holes in the forbidden zone, merging 17 billion light-years away. One possibility. These weren't normal black holes. They were primordial black holes formed in the early universe. But there's another explanation gaining traction among quantum gravity theorists. What if they were white holes? The gravitational wave signal from a white hole merger would be nearly identical to a black hole merger. The spacetime curvature is the same. The orbital dynamics are identical.
We'd only notice differences in the detailed waveform during the final moments of merger, differences that current detectors might not have the sensitivity to detect. The evidence extends beyond anomalous signals into the realm of cosmology itself. The universe's large-scale structure, how galaxies cluster into filaments and voids, contains patterns we don't fully understand.
Computer simulations that include white holes as matter sources produce distributions that better match observations than simulations with black holes alone.
To understand white holes, we must understand how quantum mechanics transforms our picture of black holes.
In classical general relativity, a black hole singularity is a point of infinite density where physics breaks down. But quantum mechanics doesn't allow infinities.
Loop quantum gravity, one of the leading theories attempting to unify quantum mechanics with gravity, suggests spacetime itself is quantized.
Space comes in discrete chunks, like pixels in an image.
At the Planck scale, about 10 to 35 meters, spacetime has a granular structure.
At this scale, the singularity isn't a point of infinite density.
It's a region of maximum possible density, compressed to the Planck density of about 1096 kilograms per cubic meter. Beyond this, quantum effects prevent further collapse.
Carlo Rovelli's calculations show that at these extreme densities, quantum tunneling becomes possible.
Just as an electron can quantum tunnel through a barrier it classically couldn't surmount, the entire spacetime geometry can quantum tunnel through the singularity, emerging on the other side with reverse time orientation.
The black hole becomes a white hole. The transformation is probabilistic.
For a stellar mass black hole, the probability per unit time is infinitesimally small, hence the 10,100-year timescale. But for primordial black holes with smaller masses, the probability increases dramatically. Some could transform in mere billions of years.
Hal Haggard calculated the detailed dynamics.
The transition occurs in two phases.
First, the black hole evaporates through Hawking radiation until it reaches a critical mass. Second, quantum tunneling flips the geometry.
The entire process takes longer than the current age of the universe for large black holes, but could happen on observable timescales for primordial black holes formed in the early universe.
Not all physicists accept this picture.
String theory, the other major approach to quantum gravity, suggests different possibilities. String theorist Juan Meldacena argues that black holes never truly form.
From an external observer's perspective, matter never crosses the event horizon. It appears to freeze at the surface, time dilated to eternity. The black hole is actually a fuzzball of strings at the would-be horizon, with no interior at all. In this view, white holes are even less necessary. There's no singularity to tunnel through because there's no singularity at all. The information paradox is resolved because information never enters the black hole, it's encoded in the fuzzball surface.
But the fuzzball model has problems.
It predicts deviations from general relativity that we haven't observed. Merging black holes should behave differently than LIGO detects. The theory needs additional mechanisms to match observations. Meanwhile, Roger Penrose proposes a third possibility: conformal cyclic cosmology. In this model, the universe undergoes infinite cycles. Each cycle ends in a Big Bang that's simultaneously the infinite future of the previous cycle. White holes might be remnants from the previous universe, bleeding through into ours. Abeyash Tekar at Penn State has developed yet another framework. His calculations in loop quantum cosmology suggest the Big Bang itself might be a white hole, the other end of a black hole that formed in a previous universe. Our entire universe could be the interior of a white hole, expanding as material expels from the horizon in the previous universe's spacetime. This forces us to reconsider fundamental assumptions about causality, time, and the origin of existence itself. The next decade will bring unprecedented observational capabilities. The instruments coming online could definitively detect white holes if they exist. The Laser Interferometer Space Antenna (LISA) will launch in the mid-2030s. This space-based gravitational wave detector will be sensitive to lower frequencies than LIGO, detecting mergers of massive black holes in the centers of galaxies. More importantly, it will detect the subtle differences in gravitational wave signatures that distinguish white hole mergers from black hole mergers.
The key difference appears in the ring-down phase, the final moments after merger when the combined object settles into its final state. A black hole rings like a struck bell at characteristic frequencies determined by its mass and spin. A white hole should ring at slightly different frequencies, offset by quantum effects at the horizon.
LISA's sensitivity should be sufficient to detect these differences. Within a decade of operation, we'll know if white holes participate in cosmic mergers. The Square Kilometre Array, scheduled to begin observations in 2027, will detect fast radio bursts with unprecedented precision. This radio telescope array will span continents, providing resolution sufficient to pinpoint FRB sources to specific regions within host galaxies. More crucially, it will detect thousands of bursts per year, building statistical distributions. If white holes produce some fraction of FRBs, the SKA will reveal characteristic patterns. The team at Oxford has predicted specific spectral signatures and timing distributions that would confirm white hole origins. By 2035, we should have definitive answers about the FRB connection. The James Webb Space Telescope continues revealing impossibly early galaxies. Each detection provides more data about the early universe's mass distribution. If these objects are white holes expelling material, they should show characteristic properties. Unusual chemical compositions, lack of old stars, absence of supermassive black holes at their centers. JWST spectroscopic observations can test these predictions. In September 2024, preliminary results suggested several of the earliest detected objects show anomalous chemical abundances, ratios of elements that don't match any stellar population models. This might indicate material expelled from a white hole rather than produced by stars. If white holes exist and we can locate them, the implications extend beyond pure science. General relativity permits solutions where white holes and black holes connect through Einstein-Rosen bridges wormholes. While classical wormholes collapse too quickly for anything to traverse them, quantum effects might stabilize a white hole-black hole connection. Kip Thorne's calculations from the 1980s showed that exotic matter with negative energy density could hold a wormhole open. We now know such matter exists in the form of Casimir effect. Quantum fluctuations create negative energy density between closely spaced conducting plates. The question is whether nature produces this effect at the scales necessary. If a stable wormhole connected a black hole to a white hole, you could potentially enter one and exit the other. The journey would be extraordinarily dangerous. Tidal forces would tear apart any normal matter. But information could traverse. Signals could pass through. More speculatively, if we understood the quantum tunneling mechanism that transforms black holes into white holes, we might learn to manipulate it. Creating microscopic black holes is theoretically possible with sufficient energy. If we could force the transformation to white holes on human timescales, we'd have access to a fundamentally new physics. The energy implications are staggering. A white hole expelling matter converts rest mass to kinetic energy with nearly 100% efficiency, far beyond anything fusion or fission can achieve. A small white hole could power human civilization for millennia. But these remain speculations. The physics is solid in principle but practically unreachable with current technology. Still, the mere possibility drives research forward. Recent breakthroughs suggest we're closer to answers than many realize. In November 2024, a team at the Max Planck Institute for Gravitational Physics published simulations of black hole to white hole transitions using loop quantum gravity. For the first time, they modeled the complete transformation process, tracking the quantum tunneling event and its aftermath. Their results predict observable signals. During the transition, which takes place over a period of seconds to hours depending on the black hole's mass, the object should emit a characteristic burst of gravitational waves. The frequency and amplitude depend on the mass and angular momentum, but the signal would be unmistakable. Crucially, these gravitational waves should arrive slightly before electromagnetic signatures, gamma rays and X-rays from expelled matter. This temporal ordering would distinguish white hole formation from any other astrophysical process. LIGO and Virgo are being upgraded to improve sensitivity. When they come back online in 2025, they'll be capable of detecting these predicted signals out to billions of light-years. If primordial black holes are transforming into white holes at the predicted rate, we should detect several events per year. In theoretical physics, multiple groups are now taking white holes seriously.
Papers discussing white hole thermodynamics, quantum information in white hole spacetimes, and observational signatures appear monthly in top journals.
The field has achieved critical mass. What seemed impossible decades ago is now simply unknown. We've moved from dismissing white holes as mathematical artifacts to actively searching for them in observational data. The universe, it seems, is stranger than we imagined.
And we're finally developing the tools to see just how strange it truly is.
White holes force us to confront the most fundamental questions about reality. What is time? Why does it flow forward? What is causality?
In classical physics, time is absolute. It flows at the same rate everywhere, proceeding inexorably from past to future. But general relativity destroyed this simple picture.
Time is relative, flowing at different rates in different gravitational fields.
Near a black hole's event horizon, time slows to a crawl.
At the horizon itself, time appears to stop entirely from an external observer's perspective. White holes invert this relationship.
At a white hole's horizon, time flows backward relative to distant observers. Events inside the white hole occur before their causes.
Effects precede their origins. This seems to violate causality, the principle that causes must precede effects. But it doesn't, quite. The key is perspective.
From inside the white hole, time still flows forward locally. Causality is preserved. It's only when you compare clocks at different locations that the reversal becomes apparent.
Think of it this way.
A black hole is a region where all possible futures lead inward.
You can enter but never leave.
A white hole is a region where all possible pasts lead outward.
You can exit but never enter. The past is sealed off, inaccessible, as thoroughly as a black hole's future interior is inaccessible from outside.
But this raises profound questions.
If white holes expel matter, where does that matter originate? From the black hole's past? From another universe? From quantum fluctuations at the singularity? The most profound implications emerge when we consider the Big Bang itself.
The universe's white hole, 53:00-55:30, multiple theorists now suggest our universe's beginning might be a white hole event.
Think about the Big Bang's characteristics.
All matter and energy emerged from a singularity. Space expanded rapidly, carrying material outward.
We cannot access anything before the Big Bang, the direction in spacetime is sealed off, just as a white hole's past is inaccessible. Abeyashtekar's calculations in loop quantum cosmology model the Big Bang as a big bounce, a transition from a contracting universe to an expanding one. The bounce occurs when density reaches the Planck limit.
Quantum gravity effects halt the collapse and initiate expansion.
But mathematically, this bounce is identical to a black hole to white hole transition. The contracting phase is the black hole. The bounce is the quantum tunneling. The expanding phase is the white hole.
Our entire observable universe might be the interior of a white hole, still expelling material from that ancient transition. This would explain several cosmic mysteries.
Why is the universe's matter-antimatter ratio imbalanced? Because the transition preferentially expelled matter over antimatter. Why is the cosmic microwave background so uniform? Because it represents material expelled from the same initial state. Why does the universe expand? Because it's still in the explosive expansion phase of the white hole transition. The model even explains dark energy, the mysterious force accelerating cosmic expansion. If the universe is a white hole, dark energy might be the quantum pressure from the transition event, still pushing outward billions of years later. But if our universe is a white hole, where is its black hole? The model suggests it existed in a previous universe, one that underwent gravitational collapse. Our universe emerged from that collapse, connected through the quantum geometry of spacetime. This raises the ultimate question. Is this process eternal? Does every black hole eventually become a white hole that births a new universe? Is the cosmos an infinite chain of universes giving birth to universes, each emerging from the collapsed remnants of its predecessor? We face limits to what we can ever know. Even if white holes exist, some questions might be fundamentally unanswerable. We cannot observe inside a white hole.
By definition, information cannot travel from the interior to the exterior. That's what makes it a white hole. We can only observe the matter and energy it expels. The white hole's interior remains forever hidden, sealed off by the mathematics of spacetime curvature. Similarly, if our universe is a white hole, we cannot access whatever existed before the Big Bounce. That information is causally disconnected from us, locked away behind a horizon we can never cross.
The previous universe, if it existed, is fundamentally unknowable. This limitation is not merely technological. It's not that we lack sufficiently powerful telescopes or sensitive instruments.
It's that the structure of spacetime itself prohibits the information transfer. The knowledge we seek exists on the other side of an impassable barrier written into the fabric of reality.
Yet even facing these limits, we're not powerless. We can still make predictions, test hypotheses, observe consequences. White holes, if they exist, leave signatures we can detect. They interact with our universe in measurable ways. The challenge is recognizing those signatures when we see them. Consider the possibility that we've been detecting white holes for decades without recognizing them. GRB 060614. FRB 121102. The cosmic microwave background cold spot. The impossibly massive early galaxies.
Each could be a white hole announcement, a message from the other side of spacetime's horizon.
Or they could be conventional astrophysics we don't yet fully understand. Unusual but explicable stellar deaths. Exotic magnetar behavior. Statistical fluctuations in the cosmic background. Efficient early star formation. The question is which explanation is correct. And more fundamentally, how do we know? What observation would definitively prove white holes exist? What could we see that would eliminate all reasonable doubt? The answer might come soon. LISA's gravitational wave observations. The Square Kilometre Array's radio surveys. JWST's deep field observations. Within the next decade, we'll have data sufficient to confirm or refute white hole existence. If they exist, we'll know. The universe will have revealed one of its deepest secrets. And we'll be forced to reimagine our place in a cosmos far stranger than we conceived. We began with a question. Could the universe contain objects that expel rather than attract? Regions where time runs backward and causality breaks down? The journey through evidence has been remarkable. Anomalous gamma-ray bursts that defy explanation. Fast radio bursts from empty regions of space. Cosmic microwave background patterns that shouldn't exist. Impossibly massive early galaxies. Gravitational wave signals from forbidden mass black holes. Each observation nudges us toward a radical conclusion. White holes might not merely be possible. They might be common. We might live in a universe thick with these cosmic fountains, expelling material from ancient black holes or even from previous universes entirely. The theoretical framework has matured. Loop quantum gravity provides a mechanism for black hole to white hole transitions. The mathematics are rigorous. The predictions are testable. What seemed like fantasy decades ago is now serious physics, published in top journals and discussed at major conferences. The implications stretch beyond astrophysics into philosophy and even theology. If the universe itself is a white hole, if existence emerged from a previous collapse, if this cycle repeats eternally, then creation becomes a process rather than an event. The cosmos reproduces itself, each generation birthing the next through the quantum tunneling of spacetime geometry. Current scientific consensus remains cautious. Most astronomers acknowledge white holes as mathematical possibilities but await observational confirmation. The standard interpretation of gamma-ray bursts and fast radio bursts invokes conventional astrophysics, stellar deaths and magnetars. The cosmic microwave background anomalies might be statistical flukes. The early galaxies might reveal efficient star formation rather than white hole fountains. But the alternatives are weakening. Each new observation eliminates conventional explanations. Each theoretical advance strengthens the white hole hypothesis. The weight of evidence shifts gradually but perceptibly toward a universe richer and stranger than the one we knew. Within a decade, we'll know. Next-generation instruments will provide definitive data. Either white holes will reveal themselves unmistakably, or the observations will demand we look elsewhere for explanations. Either outcome advances knowledge. Either answer teaches us something profound about reality's deep structure. The universe is vast. Its phenomena span scales from quantum foam to cosmic superclusters. Its history stretches from the Big Bang's first microsecond to a future trillions of years hence. And within this immensity, white holes, if they exist, occupy a unique position. They are the places where physics reaches its extremes. Where quantum mechanics and relativity merge. Where time reverses its arrow and causality breaks down. Where the unknowable past connects to the observable present. They are, quite literally, the universe's fountains, points where existence itself springs forth from behind an impenetrable horizon, carrying messages from realms we can never directly access. The mysteries are endless. The journey continues. And somewhere out there, perhaps, a white hole is forming. A primordial black hole completing its billion-year transformation. Space-time geometry quantum tunneling through the singularity. The event horizon reversing polarity. And in seconds or hours, matter compressed for eons will explode outward into space, announcing to anyone watching that the universe is capable of miracles we're only beginning to comprehend. We watch. We wait. We wonder. The universe has kept this secret for 13.8 billion years. But secrets, eventually, must be revealed. And when this one emerges, if it emerges, everything changes. Until then, we have the mathematics. The observations. The tantalizing hints that reality is stranger than we know. And the certain knowledge that the universe delights in surprising us when we least expect it. Look up tonight. Somewhere in that darkness, a gamma-ray burst might announce a transformation. A fast radio burst might carry a message from the other side of spacetime. A white hole might be born. The cosmos is vast. The journey continues. And the best discoveries, the ones that reshape our understanding, are always the ones we didn't see coming. There are approximately 200 billion trillion stars in the observable universe. Around each star, planets. On some of those planets, conditions suitable for life. The mathematics are overwhelming. The universe should be teeming with civilizations. Yet we hear nothing. See nothing. Detect nothing. In 1950, physicist Enrico Fermi asked a simple question over lunch. Where is everybody? 7 decades later, we still have no answer. But what we've discovered searching for that answer is far more disturbing than mere silence. The numbers suggest we should have detected thousands of alien civilizations by now. Some should be millions of years more advanced than us. They should be impossible to miss, their technology reshaping galaxies, their signals flooding the cosmos. The silence isn't just puzzling. It's terrifying. Because the most likely explanation suggests that something stops civilizations from reaching the stars. Something universal. Something inevitable. Something we might be approaching right now. Today, we examine the evidence for the Great Filter, the barrier that prevents intelligent life from spreading across the universe. And we confront the question that keeps scientists awake at night. Is the filter behind us, or ahead? Prepare yourselves. We begin. In 1961, astronomer Frank Drake created a simple equation to estimate the number of detectable alien civilizations in our galaxy. The Drake equation multiplies several factors. The rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction where life develops, the fraction where intelligence evolves,
the fraction that developed detectable technology, and how long those civilizations remain detectable. When Drake first calculated these numbers with conservative estimates, he got a result of about 10,000 detectable civilizations in the Milky Way alone. Today, with data from the Kepler Space Telescope and decades of exoplanet discoveries, we can refine these estimates.
We now know that virtually every star has planets.
Rocky planets in habitable zones appear around at least 20% of Sun-like stars. That's 40 billion potentially habitable worlds in our galaxy alone. Even if only 0.1% of those worlds develop life, and only 0.1% of those develop intelligence, and only 0.1% of those develop technology, we should still have 4,000 technological civilizations in the Milky Way right now.
Where are they? Since 1960, we've conducted systematic searches for alien signals.
The SETI Institute has examined millions of stars across thousands of hours of observation. Radio telescopes have scanned the sky for artificial signals, narrow-bandwidth transmissions that couldn't occur naturally. We've looked for optical laser pulses, infrared waste heat from massive engineering projects, spectral signatures of industrial pollution in exoplanet atmospheres.
We've found nothing. No signals. No evidence of vast structures. No signs of galaxy-spanning civilizations reshaping stars to their needs.
In 2015, astronomers examined 100,000 nearby galaxies for signs of Kardashev Type 3 civilizations, species that harness the energy of entire galaxies.
The search looked for excess infrared radiation that would result from massive energy use. Of 100,000 galaxies, 0 showed unambiguous signs of galactic-scale engineering.
The Breakthrough Listen project, funded with $100 million and using the most sensitive equipment ever built, has surveyed thousands of nearby stars. After scanning over 1 million individual frequency channels, they've detected no confirmed artificial signals.
The universe appears empty. Sterile. Silent. Here's what makes this truly disturbing. The universe is 13.8 billion years old. Our Sun formed 4.6 billion years ago. But Sun-like stars have been forming for over 10 billion years.
Some planetary systems are twice as old as Earth. If intelligent life emerged on a planet just 1 million years before it did on Earth, a tiny fraction of cosmic time, that civilization would now have a million-year head start on us.
Consider what humans achieved in just 10,000 years, from agriculture to spaceflight.
Extrapolate that progress over 1 million years.
Such a civilization would have technology indistinguishable from magic. They could reshape solar systems,
build structures visible from other galaxies,
spread across billions of stars.
Even traveling at just 1% of light speed, easily achievable with known physics, a single civilization could colonize the entire galaxy in roughly 50 million years.
That's less than 1% of the Milky Way's age.
The galaxy is 13 billion years old.
There's been time for colonization waves to sweep across it dozens of times over. Yet we see no evidence that this ever happened. No ancient artifacts on Mars.
No inexplicable structures orbiting distant stars. No megastructures blocking starlight in suspicious patterns.
The absence is profound, deafening, and it demands explanation. But the evidence forces us to confront an uncomfortable possibility. Something prevents civilizations from spreading. Something blocks the path from planet-bound life to galaxy-spanning empire. In 1996, economist Robin Hanson proposed the Great Filter hypothesis. The idea is simple but chilling. There must be at least one extremely difficult step in the evolution from non-life to galaxy-spanning civilization. A filter so effective that almost nothing passes through it. Think of it as a cosmic bottleneck. Millions of species might reach that point. Almost none get through. The filter explains the Fermi paradox perfectly. We don't see alien civilizations because something stopped them. They didn't survive long enough to become visible. They hit the filter and died out. But here's the terrifying part. We don't know where the filter is. It could be behind us in our past. Maybe the emergence of life is incredibly rare. Maybe the evolution of intelligence almost never happens. Maybe Earth got extraordinarily lucky, and we're genuinely alone in the galaxy. Or it could be ahead of us in our future. Maybe every civilization reaches a certain level of technology and then destroys itself. Maybe there's a universal trap that advanced civilizations fall into. Maybe we're about to hit it. This is the great filter problem. And the answer determines humanity's future. Let's examine potential filters in our evolutionary history, events so unlikely they might occur only once per galaxy. The origin of life. Abiogenesis, life from non-life, might be extraordinarily rare. We know it happened on Earth about 3.8 billion years ago, relatively quickly after the planet cooled. But we have exactly one example. We don't know if life is common or miraculous. Laboratory experiments can create amino acids and other organic molecules under early Earth conditions. But creating self-replicating systems with heredity remains beyond our capabilities. The gap between chemistry and biology might be vast. If this is the filter, we're safe. Life is the rare event, but once it exists, intelligence and technology follow naturally. We passed the filter billions of years ago. Eukaryotic cells. For 2 billion years, life on Earth consisted entirely of bacteria. Then, about 1.8 billion years ago, complex cells evolved, cells with nuclei and specialized organelles. This happened through endosymbiosis. One bacterium engulfed another, and instead of digesting it, they merged. This event appears to have occurred exactly once in Earth's history. Every complex organism, plants, animals, fungi, descends from that single merger. It took half of life's history on Earth to happen. That suggests it's extremely improbable. If this is the filter, we passed it. Eukaryotes exist. The universe might be full of bacterial life but devoid of anything complex. Intelligence. Dinosaurs ruled Earth for 165 million years and never developed technology. Intelligence of the human type, abstract reasoning, language, toolmaking might be vanishingly rare even among complex life. Earth has hosted billions of species over billions of years. One became technological. That's a success rate of 0.000000001%. Even on a planet teeming with life, intelligence might almost never emerge. Technological civilization. Even intelligence doesn't guarantee technology. Dolphins are intelligent. Octopi solve complex problems. Crows use tools. But none developed writing, mathematics, or science. The window might be narrow. Intelligence must be precisely calibrated, smart enough to manipulate the environment but not so intelligent that cooperation becomes impossible. Social structures must evolve to support knowledge transfer. Environmental conditions must reward innovation. If any of these is the filter, the news is good. We've already passed it. The galaxy might be sterile, but Earth is special. We're the 1 in a billion exception that made it through. But here's where it gets disturbing. Nuclear weapons. In 1945, humanity developed the ability to destroy itself. Within decades, we built arsenals sufficient to end civilization multiple times over. The Cold War brought us within minutes of annihilation on several occasions. In 1983, Soviet early warning systems detected incoming American missiles. LT call. Stanislav Petrov, on duty that night, had seconds to decide whether to report the attack, which would have triggered automatic retaliation. He judged it a false alarm. He was right. A software glitch had misidentified sunlight reflections as missiles. One man's intuition prevented nuclear war. We survived by chance. Every technological civilization might reach this point, the moment when they can destroy themselves, and nearly do. Most might fail Petrov's test. The galaxy might be littered with radioactive ruins of species that didn't get lucky. Biological weapons. Synthetic biology is advancing exponentially. CRISPR gene editing costs thousands of dollars and requires minimal training.
Within decades, designing novel organisms will be accessible to individuals. In 2012, researchers created a modified H5N1 flu virus that spread between ferrets through the air. The modified virus had a 60% fatality rate. The experiment proved that deadly pandemics could be engineered. What happens when this technology becomes commonplace? When a single malicious individual can engineer and release a civilization-ending plague? When accidents in thousands of laboratories worldwide could unleash extinction? Maybe every civilization reaches this level and someone, through malice or accident, releases something unstoppable. Artificial intelligence. In the next few decades, we may create artificial general intelligence systems that match or exceed human cognitive abilities. Such systems could improve themselves, leading to recursive self-improvement and superintelligence. A superintelligent AI with goals misaligned with human survival could eliminate us efficiently and thoroughly. Not through malice, just indifference. Like we don't worry about ants when constructing buildings. The alignment problem, ensuring AI systems reliably share human values, remains unsolved. Many researchers believe it's extraordinarily difficult. If every civilization creates AI before solving alignment, every civilization dies. Climate change and resource depletion. Industrial civilization requires massive energy inputs. On Earth, we're burning through fossil fuels laid down over millions of years. We're changing the climate, depleting aquifers, destroying ecosystems. Maybe this is universal. Maybe every civilization industrializes, exhausts its planet's resources, triggers ecological collapse, and falls back to pre-technological subsistence. They never reach the stars because they destroy their homeworld first. The Great Filter Synthesis. Here's the most disturbing possibility. The filter isn't one thing. It's many things. A gauntlet of barriers, each difficult to pass. Origin of life is rare. Complex cells are rarer. Intelligence is rarer still. And even if you beat all those odds, technology brings existential risks. Nuclear war. Engineered pandemics. Rogue AI. Ecological collapse. One mistake and you're extinct. The universe might be full of dead worlds. Planets where life began but never complexified. Planets with bacteria but no animals. Planets where intelligent species arose but never developed technology. And the rare technological species? They destroyed themselves within centuries of industrialization. We might be living in a cosmic graveyard, surrounded by the ruins of a billion failed attempts at reaching the stars. Exoplanet statistics. The Kepler mission revolutionized our understanding. Between 2009 and 2018, Kepler discovered over 2,600 confirmed exoplanets. Statistical analysis suggests 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone. That's 40 billion Earth-like planets in our galaxy alone. If even a tiny fraction develops life, the galaxy should be teeming with it. In 2022, the James Webb Space Telescope began examining exoplanet atmospheres. Within a year, JWST detected water vapor, carbon dioxide, and methane on multiple worlds. The chemical building blocks of life are common. This makes the silence more paradoxical. The ingredients are everywhere. The opportunities are endless. Where are the civilizations? Biosignatures. In September 2020, astronomers announced the detection of phosphine in Venus's atmosphere, a gas produced primarily by biological processes on Earth. The discovery sparked intense debate. Follow-up observations complicated the picture, and the jury remains out. But the episode demonstrated our capability. We can now detect gases in the atmospheres of planets dozens of light-years away. If industrial civilizations exist nearby, we should detect their pollution, chlorofluorocarbons, nitrogen oxides, or other artificial compounds. We've examined dozens of promising worlds. We've found nothing artificial. Nothing that couldn't be explained by geology or chemistry alone. Technosignatures. In 2015, astronomers detected unusual light fluctuations from KIC 846-2852, nicknamed Tabby's star. The star dimmed irregularly by up to 22%, far more than any planet could cause. Some speculated about a Dyson swarm, a megastructure built to harvest stellar energy. Years of observation and analysis ultimately pointed to a dust cloud, probably from a disintegrated comet.
Nature, not engineering.
In 2017, the interstellar object Oumuamua passed through our solar system. Its elongated shape and unexpected acceleration led some to speculate about artificial origin.
Again, further analysis suggested natural explanations, outgassing from a comet-like body. We keep searching for artifacts and keep finding natural phenomena. The universe is strange, but not artificial.
The accumulating evidence paints a picture.
Life's ingredients are common.
Habitable worlds are plentiful. Yet we detect no life beyond Earth, no intelligence, no technology.
This suggests the filter is real and extremely effective.
But it doesn't tell us where the filter is. If the filter is behind us, we're miraculous survivors.
Earth is extraordinarily special.
Life might be common, but intelligence and technology are vanishingly rare.
We might be the only technological civilization in the observable universe. That's lonely but safe. Our future is secure.
We can spread across the galaxy without competition.
In a billion years, our descendants might fill the cosmos.
If the filter is ahead of us, we're in danger.
Every civilization reaches our level and then dies.
We're approaching the barrier that ended countless species before us.
Within centuries, maybe decades, we'll face the test that almost nothing passes. The evidence doesn't clearly favor either possibility.
But some researchers argue we should hope the filter is behind us.
Because if it's ahead, our survival becomes unlikely. Nobel laureate Enrico Fermi recognized this in 1950. The silence isn't just a puzzle. It's a warning. We began with a question. Where is everybody? 7 decades of searching have yielded no answers. Radio silence. Empty skies. No vast empires. No ancient artifacts. No signals from the stars. The mathematics say the universe should be crowded. The observations say it's empty.
The Great Filter hypothesis reconciles this paradox.
Something prevents life from spreading.
Something extraordinarily difficult to overcome.
If we're extraordinarily lucky, the filter is behind us. Life is rare. Intelligence is rarer.
We're special, perhaps unique, and the galaxy is ours to inherit.
If we're typical, the filter is ahead.
We're heading toward a barrier that destroyed every species that reached it before us.
Nuclear war. Engineered pandemic. Rogue AI. Ecological collapse.
Something kills technological civilizations reliably and thoroughly.
Current evidence doesn't let us distinguish between these possibilities. We don't know if we're special or doomed. We don't know if our future holds galactic empire or imminent extinction.
But the search continues.
SETI examines millions of stars. JWST studies exoplanet atmospheres. Breakthrough Listen scans for artificial signals. Every observation that finds nothing makes the paradox deeper and the filter more ominous. The most profound implication. The silence itself is data. Every year we don't detect aliens updates our understanding.
The filter must be severe. The barriers must be formidable.
Most species don't make it. The question before humanity is simple. Will we?
We've survived nuclear weapons for 80 years.
We're developing synthetic biology and artificial intelligence.
We're changing our planet's climate. We're approaching, or already facing, the filters that might have destroyed every species that came before.
The universe watches.
Waits. Maintains its terrible silence.
And somewhere in that darkness, on uncounted worlds orbiting distant stars, perhaps other species face the same test. Perhaps they wonder, as we do, whether they're alone. Perhaps they search the sky for signals and find only emptiness. Perhaps they fear, as we should fear, that the silence is an answer. That the universe is empty because nothing survives the filter. That intelligence carries the seeds of its own destruction. We don't know. We can't know. Not yet. But we'll find out. One way or another, within the next few centuries, humanity will discover where the filter lies. We'll either pass through it and begin spreading across the galaxy, or we'll join the silence. Become another cautionary tale in a universe full of failed experiments. The great filter is real. The evidence demands it. The only question is, have we already passed it, or is it waiting ahead? Look up tonight. The stars remain silent. And that silence might be the most important message we'll ever receive. The universe is vast. The mysteries are endless. And the answer to Fermi's question might be the most important truth humanity ever learns. The journey continues. The search goes on. And every day we survive is one more day closer to knowing whether we're the exception or the rule.